Far beyond our solar system, a quiet world circles an old orange star. It may have deep oceans, a stable climate, and conditions where life could survive for billions of years. From a distance, it looks almost perfect. But this world is larger and heavier than Earth, and everything on its surface is held down by a much stronger pull. A rocket that could reach orbit here might never escape there. More speed requires more fuel, and that fuel adds weight until the vehicle becomes too large to build. A civilization could study the stars, understand the universe, and still remain trapped beneath its own sky. So tonight, the question is simple. Could the planets best suited for life also be the hardest worlds to escape? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. Would you live on a perfect planet if you knew no one could ever leave it? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about why the most habitable planets may be impossible to escape. Far beyond the familiar planets of our solar system, a small orange star moves quietly through the galaxy. It is cooler than the sun and less brilliant, but it burns with a steady light that may continue for far longer. Around it travels a world only slightly wider than Earth, too distant to appear as anything more than a faint disturbance in the star's glow. No telescope can show its coastlines or clouds, yet the measurements suggest something unusually promising. The planet completes each orbit at a comfortable distance from its star. It is not scorched by overwhelming heat, and it is not buried beneath permanent global ice. Its year may be shorter than ours because the orange star shines more gently, allowing the world to remain closer without becoming too warm. From space, if we could see it clearly, the planet might look calm and familiar, a sphere of ocean, weather, and dark land moving beneath a softer sun. Nothing in the data would prove that life exists there. A planet can orbit in the right region and still be dry, poisonous, or hidden beneath an atmosphere too dense for a solid surface to be reached. Even the word habitable describes a possibility, not a discovery. It means that some conditions may allow liquid water and familiar chemistry, not that forests are waiting below the clouds. But suppose the observations continue and the world survives each careful test. Its mass suggests a rocky interior rather than a small gas planet. Light passing through its atmosphere carries signs of water vapor, carbon dioxide, and a pressure that could keep oceans stable. The star appears mature and comparatively quiet. The orbit is nearly circular, avoiding extreme changes between heat and cold. Slowly, the distant point begins to resemble a place where life could have had a very long time to begin. A planet like this would not need to be a copy of Earth. Its oceans could cover more of the surface, broken by broad chains of islands and low continents. The atmosphere might hold thicker clouds, moving through wide belts under a sky of unfamiliar color. Rain could fall for weeks over warm seas, while dry regions formed deep inside the largest landmasses. The details remain unknown, but the world could offer far more stable living space than the narrow image of a perfect second Earth suggests. Its orange star would hang larger in the sky than the sun appears from Earth, though its light might feel warmer in color and gentler in intensity. Daylight could have a muted golden cast. Plants, if anything like plants evolved there, might use pigments tuned to a different spectrum, covering the land in colors that would not match our familiar green. Life would not need Earth's appearance to use the same basic gifts of energy, liquid, and time. Time may be the most important gift. On Earth, complex life required billions of years to develop, repeatedly interrupted by impacts, climate shifts, and mass extinctions. A stable planet around a long-lived star could remain suitable for life across a much wider span. Oceans might survive while evolution explored possibilities that never appeared here. A world older than Earth could have been biologically active before the Sun and planets formed. From the upper atmosphere, the planet might seem peaceful. Clouds would curve across an enormous horizon, and the surface below would turn slowly from daylight into night. Perhaps faint storms would flash over the oceans. Perhaps the dark side would carry no artificial light at all. Or perhaps a thin network of illumination would reveal that biology had already become technology. Moving lower, the difference between this world and Earth would begin to make itself felt. The air might be denser, pressing more firmly against anything descending through it. A spacecraft would heat as it entered, surrounded by glowing gas before parachutes or engines could slow the fall. The same atmosphere that sheltered life from radiation and helped distribute warmth would make arrival more demanding. Then the vehicle would touch the ground, and the deeper difference would become impossible to ignore. The planet is larger because it contains more mass. Its surface stands farther from the center than Earth's surface does, which weakens gravity somewhat, but the added material below may more than compensate. A person could weigh noticeably more here, even if the landscape looked gentle and the air remained easy to breathe. Movement would not necessarily be unbearable. Life born on this world would know no other gravity. Bodies might grow shorter, broader, or more strongly supported, though evolution offers no single required design. Trees could rise differently, animals could distribute their weight across more limbs, and flight might depend on the help of a dense atmosphere. Nothing would experience the gravity as a prison. It would simply be part of the environment, as ordinary as Earth's downward pull is to us. The landscape itself would carry the same quiet influence. Very tall mountains may be less common because greater weight makes rock deform and collapse more readily over geological time. Valleys could be broad, coastlines shallow, and rivers, slow as they crossed, low ground toward the sea. These possibilities would depend on the planet's crust, heat, water, and history. But gravity would shape every horizon without appearing as a visible object. An ocean, on such a world, could be deeper than any sea on Earth. Greater gravity would increase pressure quickly below the surface, while the planet's water supply might cover most of the continents before they ever rose above the waves. Life could thrive across bright upper waters and dark layers far below, separated by conditions that made travel between them difficult. The world might contain immense biological richness, while offering little dry land for fire, industry, or cities. Or the balance could be unusually favorable, enough water to stabilize climate, but not enough to drown the rock. Long coastlines could connect oceans with mineral-rich land. Volcanoes and weather would recycle materials. A magnetic field generated within the planet might help protect the atmosphere, while steady internal heat continued driving geology. There is no guarantee that greater mass creates these advantages, but it can allow a world to hold energy and material for a very long time. If intelligent life appeared there, its earliest view of the universe would come from beneath this heavy sky. The stars would still turn overhead. The nearby moon, if the planet possessed one, might cross the orange sun and pull against the oceans. Careful observers could measure the paths of planets, discover that their world was round, and eventually understand that gravity connected the falling of an object to the movement of bodies across space. Their science could advance without leaving the ground. Telescopes would reveal distant galaxies. Radio instruments could listen through the atmosphere. Mathematics would describe orbits that no traveler had entered. The civilization might understand the age of its star, identify worlds around other suns, and calculate the exact force holding everything to the surface long before it possessed a machine capable of challenging that force. The earliest rockets might rise as ours did, beginning with experiments that barely left the ground. They would climb through clouds on pillars of fire, losing fuel with every second while gravity pulled continuously below. Some could reach the upper atmosphere. Others might trace long arcs and fall back into the ocean. Each attempt would reveal that crossing the sky is not the same as escaping the planet. From the surface, the difference might appear small. Gravity could be only somewhat stronger than on Earth, and daily technology could adapt to it. Buildings would be designed with greater support, aircraft with wider wings, and vehicles with more powerful engines. Yet orbital flight does not respond gently to small changes. A rocket must build enormous sideways speed while also climbing, and every additional requirement spreads through the entire vehicle. For the people below, space might remain visible but strangely distant. They could watch moons, predict comets, and receive light that had crossed the universe. Their instruments might even detect the atmospheres of other living worlds. Knowledge would move freely across the gap, while matter remained held down. The stars would not be hidden. They would be present every night, clear enough to understand and difficult enough to reach. This is what makes the planet unsettling. It is not a hostile world that life must escape in order to survive. It may be a generous home, with stable seas, broad habitable regions, and a star that changes slowly. There may be no urgent reason to leave. The trap, if it deserves that word, is made from the same physical conditions that help the world remain alive. A thicker atmosphere protects the surface but resists anything moving through it. Greater mass can help preserve oceans, but raises the energy needed to lift them beyond gravity. Long geological activity may support a changing, fertile world while keeping its surface firmly bound to a deep planetary interior. The qualities that make the planet dependable from below can make it unforgiving from above. For millions of years, this would not matter. Life does not need orbit. Oceans, cells, forests, and animals can flourish without placing anything beyond the atmosphere. Even intelligence can develop language, art, machines, and astronomy while remaining on the ground. The difficulty appears only when a civilization decides that understanding the sky is no longer enough. There might be no dramatic moment when its people realize they are confined. The truth could emerge through a century of engineering. Larger rockets, stronger materials, better fuels, and repeated attempts that approach orbit without making it practical. The laws would be clear, not mysterious. Their planet would not forbid escape, but it might demand machines so large, expensive, and dangerous that leaving remained a rare achievement rather than the beginning of an age in space. Earth, viewed from such a world, could seem unusually light. Our gravity is strong enough to maintain a substantial atmosphere and oceans, yet weak enough for chemical rockets to reach orbit. We do not experience this balance as remarkable, because it is the only planetary surface from which we have ever launched. Across the wider range of rocky worlds, it may be a quiet advantage rather than a universal condition. The distant planet would continue moving beneath its orange star, apparently perfect and perhaps full of life. Its clouds would pass over oceans older than human history. Its gravity would hold the atmosphere close, keep the surface stable, and pull every living thing gently but persistently downward. From far away, these would look like signs of a world that has kept everything life needs. And that may be the hidden advantage of a heavier planet. Before its gravity becomes a barrier to the sky, it can make the surface below a remarkably enduring home. A planet does not remain habitable simply because it begins with water and a mild temperature. It must keep those conditions while its star changes, its interior cools, and its atmosphere is slowly tested by radiation and impacts. Earth has managed this balance for billions of years, but not perfectly. Its climate has moved between extremes, life has endured repeated catastrophes, and the future of its surface is tied to a sun that will gradually become brighter. A somewhat larger rocky world could follow a different path. With more material beneath its surface, it may cool more slowly than Earth. Heat, left from its formation, along with heat produced by radioactive elements, could keep parts of the interior active for a longer period. This does not guarantee volcanoes or moving continents, but it gives the planet a larger reserve of energy from which long-lived geology might develop. Geological activity can help a world regulate itself. Volcanoes return gases to the atmosphere, while weathering removes some carbon dioxide from the air and carries it into rocks and oceans. Over immense spans of time, these processes can act as a rough climate control, warming a cold planet or reducing the buildup of heat. The balance is never exact, yet without some way to recycle material, a habitable surface may become only a temporary phase. On the heavier world, mountains would rise, wear down, and return to the interior through processes that might resemble those of Earth without copying them. Continents could drift, oceans could open and close, and mineral-rich material could move between the crust, water, and atmosphere. Life would receive changing environments rather than one unbroken landscape, creating both danger and opportunity across evolutionary time. The planet's greater pull could also help it retain an atmosphere. Gas molecules are always moving, and the fastest can eventually escape into space, especially when heated by radiation from the star. Stronger gravity raises the speed required to leave. Over billions of years, this can help a planet hold on to gases and water that a smaller world might gradually lose. Mars shows what the loss of protection can look like. Although its history was shaped by many factors, it is smaller than Earth, cooled more quickly, and now possesses a thin atmosphere above a cold, dry surface. Ancient channels suggest that liquid water once moved there more freely. A larger world would not automatically avoid such an ending, but its size could give it more ways to resist it. More atmosphere can make climate less fragile. Air carries heat from warmer regions toward colder ones, softening the difference between day and night and between equator and poles. On a planet that rotates slowly, a substantial atmosphere could prevent the dark side from freezing completely and the bright side from becoming unbearable. Clouds could reflect part of the incoming light, while greenhouse gases kept the surface from losing too much warmth to space. This balance would depend on composition. A thick atmosphere rich in CO2 could turn a promising world into a furnace. Too much hydrogen and helium might hide a deep ocean beneath crushing pressure or remove any accessible rocky surface. Greater gravity is good at holding gas, but it does not choose which gas remains. The same ability that preserves breathable air could build an atmosphere no familiar life could survive. There is therefore no simple line between a slightly larger Earth and a small Neptune. Two planets with the same radius can have very different interiors. One may be dense rock beneath a modest atmosphere, while another contains large amounts of water, gas, or ice. From many light years away, astronomers may know the mass and size, yet remain uncertain about what exists below the cloud tops. The most interesting world would lie in a narrow region between these outcomes. It would be massive enough to retain water and internal heat, but not so massive that a deep gas envelope separated the surface from space. Its atmosphere would be substantial without becoming crushing. Its oceans would be widespread without covering every source of exposed rock. None of these conditions is assured, but together they describe a planet that could offer life more stability than Earth. Surface area matters as well. A world wider than ours provides more room for coastlines, shallow seas, river systems, islands, and isolated habitats. If its water and land were arranged favorably, different forms of life could evolve in separate regions while remaining connected over geological time. A disaster affecting one part of the planet might leave distant ecosystems untouched, allowing recovery to begin. Greater size could also support larger oceans with more stable temperatures. Water changes temperature slowly, absorbing heat during warm periods and releasing it during cold ones. Ocean currents move that energy across the globe, reducing sudden shifts. On a planet with active geology, dissolved minerals and nutrients could continue entering the water, feeding biological cycles for ages. But an ocean world with almost no land would create a different problem. Deep water can separate the ocean from the rocky interior beneath layers of high-pressure ice, limiting the chemical exchange that life may need. Without continents, fire and some forms of technology could be difficult to develop. A planet could be excellent for simple marine life and still offer few paths toward a civilization capable of studying the sky. Habitability depends on more than the amount of life a planet can hold. It also depends on where that life can live, how often its environment changes, and whether energy and material continue to circulate. A world covered with rich oceans may be biologically successful while remaining silent to distant telescopes. Another with less total life could produce land-dwelling intelligence and technology. The word habitable hides many different futures. Protection from stellar radiation adds another layer. A magnetic field can direct some charged particles around a planet, reducing their effect on the upper atmosphere and surface. A larger, slowly cooling interior might help maintain the moving conductive material needed to generate such a field. But size alone is not enough. Rotation, composition, and the way heat moves through the interior all matter. Even without a strong magnetic field, a dense atmosphere can provide substantial protection at the surface. Life below water or underground would be sheltered further. The planet's environment may therefore remain suitable under conditions that would be dangerous on an exposed, smaller world. What appears hostile from space could still contain broad, protected regions below the clouds. The nature of the star may be as important as the planet itself. A small orange K-type star burns fuel more slowly than the sun and can remain stable for a very long time. It is brighter and generally less extreme than the smallest red dwarfs, allowing a habitable planet to orbit farther away. That distance can reduce some of the problems associated with close orbits, including powerful stellar activity and the tendency for one side of a planet to remain permanently turned toward its star. Around such a star, evolution might receive tens of billions of years rather than the shorter window available around a sun-like star. The early years could still be violent, and no star is perfectly calm, but the long middle age offers time. Complex ecosystems could rise, disappear, and rise again. Intelligence might not be a single brief experiment, but one of many possibilities explored during a planetary lifetime. An older planet could also have passed through its most chaotic period before Earth even formed. The heavy bombardment of early debris would have faded. Its orbit may have settled into a steady rhythm, and unstable neighboring worlds may already have been removed or pushed into safer paths. By the time observers on Earth detected it, the surface could have enjoyed billions of years of relative calm. Too much calm would not necessarily help. Evolution is shaped by change as well as stability. Ice ages, shifting continents, and environmental pressure open new habitats while closing others. A completely unchanging world might allow life to persist without becoming complex. The most generous planet may be one that changes slowly enough to avoid constant destruction, but often enough to keep biology adapting. This is why the idea of a world more habitable than Earth is not a search for perfection. It is a search for a slightly different balance, somewhat older, somewhat larger, perhaps warmer, and orbiting a star that gives life more time. Each difference is modest. Together, they could create a planet with a greater area of comfortable surface and a longer period during which that surface remains alive. No such world has been confirmed in all of these details. Telescopes can identify promising size, orbit, and starlight, but atmosphere and surface remain difficult to measure. Even a beautiful spectrum can be interpreted in several ways. The planet described here is not a known destination. It is a scientifically possible arrangement assembled from properties that future observations may one day find together. If such a world exists, its inhabitants may never think of their planet as unusually fortunate. The ocean continues beyond the horizon, weather moves gently through the seasons, and the orange sun changes little across recorded history. Extinctions may still occur, but the larger pattern of life remains steady. The planet offers no obvious reason to fear the future or search for another home. Its weight would be present in every part of that stability. Gravity helps hold the water close and keeps the atmosphere from thinning into space. The planet's mass carries heat within the deep interior and shapes the pressure of the oceans above. The living surface is not protected from gravity. It is partly protected by it. For most forms of life, that is an uncomplicated gift. A cell does not need to reach orbit. A forest gains nothing from escaping the atmosphere. Even a technological species may spend thousands of years benefiting from the planet's mass without confronting its deeper cost. Gravity becomes a problem only when matter must be lifted far enough and accelerated fast enough that it no longer returns. Seen from orbit, the world would still appear serene. Clouds would soften the continents, oceans would reflect the orange star, and the atmosphere would curve as a thin, bright line above the night side. Nothing in the image would reveal how much energy was required to remain at that height. The obstacle would not be visible in the landscape, yet it would extend around the entire planet. But the same mass that helps a planet hold its air, water, and warmth also deepens the invisible well beneath every living thing on its surface. That well has no visible edge. Standing beside an ocean, an observer would see only the horizon and the orange light moving across the clouds. Gravity would not appear as a wall or a force field. It would be present in the weight of the body, the fall of rain, the shape of waves, and the steady pressure carried by every structure. Nothing on the surface could point toward a place where the pull suddenly ended. Close to the ground, gravity is usually described by how strongly it accelerates a falling object. On Earth, that acceleration gives every person and machine a familiar weight. On a larger rocky planet, the value could be somewhat greater, though not simply equal to the increase in mass. The radius matters too. A wider world places its surface farther from the center, partially reducing the effect of the extra material below. This is why a planet several times more massive than Earth would not necessarily make everything several times heavier. If it is also larger, surface gravity might rise by a more modest amount. A person who would weigh 70 kilograms on Earth might feel as though they carried several extra tens of kilograms there. Uncomfortable for a visitor, but entirely ordinary for life that evolved under those conditions. The local biology would be built around that weight. Skeletons, trunks, stems, and shells would support bodies that had never known Earth's lighter pull. Muscles would develop against the same force from birth. A creature would not spend every day struggling to stand, any more than humans struggle constantly against terrestrial gravity. Evolution does not remove the force, but it shapes life that can function within it. Technology would adapt in the same quiet way. Buildings might be lower or use stronger supports. Bridges would carry their own weight differently. Cranes, elevators, and aircraft would require more power for the same task. Engineers would know these limits so well that their machines would not seem unusually heavy. The entire civilization would be designed inside the gravity, with no need to compare it with another world. Even flight might remain common if the atmosphere were dense enough. Greater air pressure can provide more lift to wings, partly compensating for the weight of an animal or aircraft. Large forms could glide on broad surfaces while storms moved through the thick sky. The details would depend on air density, body design, and speed. But strong gravity alone would not condemn the world to a motionless surface. The difference between ordinary movement and spaceflight begins with distance. Jumping, flying, or climbing only pushes against gravity for a short time. When the effort stops, the planet pulls the object back. Orbit requires something stranger. moving sideways so quickly that the surface curves away beneath the falling object. At the same rate the object falls toward it. A satellite is not floating beyond gravity. It is falling constantly. Its speed carries it around the planet before it can reach the ground. On Earth, low orbit requires roughly 8 kilometers of sideways motion every second, along with additional speed to overcome atmospheric drag and losses during ascent. The spacecraft remains deep within Earth's gravity, but it is moving fast enough to keep missing the surface. Around a heavier planet, that orbital speed would be greater. The larger world contains more mass pulling inward, so a satellite near the surface must move faster to remain in free fall around it. A small increase in the pull felt on the ground can translate into a much larger demand on a launch vehicle, because the vehicle must continue accelerating until it reaches an entirely different state of motion. Escaping the planet altogether requires more. An object must travel quickly enough that gravity can slow it forever, without ever bringing it back. This speed is known as escape velocity. On Earth, it is a little more than 11 kilometers per second when measured from the surface without help from the atmosphere or rotation. A rocket does not need to reach that exact speed at one instant, but the number reveals the depth of the gravitational well it must climb. For a substantial super-Earth, escape velocity could approach twice Earth's value. The surface might feel only moderately heavier, while permanent escape demands a speed near 20 kilometers per second or more. That difference is the hidden trap. Daily life responds to surface gravity, but spaceflight must overcome the accumulated pull of the entire planet across a great distance. Speed at this scale is difficult to picture. A passenger aircraft covers a small fraction of 1 kilometer each second. A rifle bullet may travel around 1 kilometer per second. Earth-orbiting spacecraft move several times faster than that, circling the planet in roughly an hour and a half. On the heavier world, the threshold would lie farther beyond anything familiar on the ground. The planet's rotation could offer some assistance. Earth's surface moves fastest at the equator, giving eastward launches a small but valuable beginning. A rapidly rotating super-Earth might provide a similar boost, perhaps larger if its day were short and its radius wide. But rotation has limits. A planet turning fast enough to remove most of the escape problem would approach instability at the equator, and many potentially habitable worlds may rotate more slowly than Earth. Mountains would not solve the problem either. Launching from high ground reduces the amount of atmosphere above and places the vehicle slightly farther from the planet's center. But the improvement is small compared with the total depth of the gravity well. On a high-gravity world, the tallest mountains may also be lower because rock has more difficulty supporting its own weight. The obvious path upward could be shorter precisely where it is most needed. Moons could shape the situation in complicated ways. A large moon might create tides, stabilize aspects of the planet's rotation, and eventually provide a destination close enough to inspire early exploration. Its gravity could also assist certain spacecraft trajectories after orbit had already been reached. Yet no moon can lift a rocket through the first kilometers of ascent. The main barrier remains where the journey begins. The atmosphere adds resistance, but it is not the deepest part of the trap. A launch vehicle loses energy forcing air aside, especially near the surface where density is greatest. A more massive planet might carry thicker air and stronger pressure, increasing those losses. Even so, once the vehicle climbs beyond most of the atmosphere, the planet's gravity continues. The air eventually ends. The pull does not. Gravity weakens with distance, but it never turns off. At twice the distance from the center, the pull becomes 1/4 as strong. Farther away, it continues fading, stretching outward across the entire planetary system. This gradual decline is what gives the well its shape. Leaving is not like crossing a border. It is like climbing a slope that becomes gentler without ever becoming perfectly flat. Physicists often represent this as a curve. with the surface lying deep below the level of distant space. The image is not a literal hole in the universe, but it is useful. Objects at the bottom need energy to climb. A heavier and more compact planet places the surface lower on that curve. Every kilogram of spacecraft begins deeper, and every kilogram must be carried upward with the vehicle. From orbit, the civilization's home would finally appear as a whole world. Weather systems would circle the oceans, the atmosphere would shine at the edge, and the orange star would rise without a horizon blocking half the sky. Reaching that view might become one of the greatest achievements in the planet's history. But an achievement can be physically possible while remaining too demanding to become routine. The first object placed in orbit might be tiny, carrying no passenger and operating for only a short time. Its launch vehicle could dominate the skyline, filled almost entirely with propellant. Years of industry might be consumed for a few kilograms above the atmosphere. If the mission failed, the loss would be more than financial. It could make another attempt, politically or materially difficult, for a generation. Success would not make the next launch easy. Every satellite, telescope, fuel tank, and habitat would have to cross the same well. Infrastructure in orbit could eventually help, but building it requires repeated access before the assistance exists. The civilization would face a difficult beginning, in which space technology is most useful after the hardest obstacle has already been overcome. This problem would not prevent understanding. Scientists could calculate trajectories, observe other planets, and know exactly why their machines returned to the surface. There would be no missing discovery that suddenly removed gravity. The equations might describe a reachable orbit, while also showing that the required vehicle approached the limits of available materials, engines, and industry. The planet would therefore be trapped in a practical sense before it was trapped in a physical one. Nature would not forbid escape. A sufficiently powerful system could still lift a payload away. But if that system required a significant share of the civilization's resources for every launch, space would remain a rare destination, visited through national or planetary efforts rather than ordinary technology. There is a large difference between sending one instrument into orbit and becoming a spacefaring society. The second demands reliability, repetition, and enough spare capacity to survive failure. It requires placing not only a useful payload above the atmosphere, but also the equipment, fuel, and support needed to remain there. The deeper the gravity well, the more distant that transformation becomes. For life below, none of this changes the generosity of the world. The ocean remains stable, the atmosphere remains protective, and the old orange star continues shining. The barrier appears only when intelligence tries to move matter beyond the environment that allowed intelligence to form. Paradise and confinement can occupy the same planet without contradiction. The world's inhabitants might look upward and see no prison at all. They would see weather, moons, and stars. Only their calculations would reveal the scale of the climb, showing that the surface beneath their feet lies at the bottom of a much deeper well than Earth's. The problem begins when one asks not how heavy an object feels on the ground, but how much speed it must gain before the planet can no longer pull it back. A rocket gains that speed by throwing mass in the opposite direction. Hot gas rushes from its engines, and the vehicle is pushed upward. The idea is simple enough to demonstrate with a small model, but the difficulty grows inside the fuel tanks. Every second of thrust consumes propellant, while the propellant, needed later in the flight, must be lifted during all the seconds that come before it. This means a rocket does not carry fuel only for its payload. It carries fuel for the structure, engines, tanks, and all the fuel that has not yet been burned. Adding a little more required speed cannot be solved by adding the same small amount of propellant. The new fuel adds weight, which requires still more fuel beneath it. The vehicle begins to grow through a chain in which every solution becomes part of the problem. On Earth, launch vehicles already begin almost entirely as propellant. The useful object at the top may form only a small fraction of the mass waiting on the launch pad. Most of the machine exists to accelerate itself and then be discarded. When the engines stop, the empty tanks and structures are no longer helpful, so rockets release them in stages rather than carrying dead weight all the way to orbit. Staging is one of the reasons chemical spaceflight works at all. A lower stage lifts the vehicle through the early part of the flight, empties its tanks, and falls away. A lighter stage then continues, followed by another, if necessary. Each separation improves what remains, but it also adds engines, joints, guidance systems, and moments when a failure can end the entire mission. Earth sits close to the edge of what ordinary chemical propulsion can do efficiently. Our rockets are astonishing machines, yet they devote nearly all their starting mass to escaping a planet whose gravity feels normal to us. A larger, rocky world would demand more speed from the same basic fuels, and those fuels cannot release unlimited energy simply because engineers build larger tanks. The relationship between speed and propellant is unforgiving. Doubling the speed a rocket can provide does not merely double the required fuel. Depending on the engine and vehicle, the mass can rise many times over. This exponential growth is the heart of the rocket equation, and it turns a moderate increase in escape velocity into a much larger engineering burden. Suppose the civilization wants to place a small scientific instrument into orbit. The payload itself might fit inside a room. On Earth, a large rocket could carry it with substantial effort. On a high-gravity super-Earth, the launcher might need to be comparable to the greatest machines the civilization has ever built, even though the object delivered above the atmosphere remain modest. Making the payload smaller helps, but only to a point. Sensors, transmitters, power systems, and shielding require some minimum mass. A rocket must also carry guidance, engines, and enough structure to survive its own acceleration. If the vehicle becomes enormous while the payload shrinks, the mission begins to look less like transportation and more like a rare experiment in moving a few kilograms away from the ground. Sending living passengers would be harder. A crew requires space, air, water, temperature control, communication, safety systems, and a way to return or survive in orbit. Redundant equipment adds mass, because a single failure cannot be allowed to kill everyone aboard. The rocket must lift not only bodies but a small protected environment, and every kilogram of that environment creates more vehicle below it. The launch pad would have to withstand an immense release of energy. Engines powerful enough to lift the vehicle must produce more thrust than its weight from the moment it leaves the ground. On a heavier planet, each kilogram contributes more weight, so more engines may be needed before any upward movement begins. Those engines add mass, require pumps and fuel lines, and expose the vehicle to additional points of failure. There is also a practical limit to how many engines can work together beneath one rocket. Their exhaust must leave without destroying neighboring machinery. Vibrations pass through the structure. Control systems must balance the thrust, and the failure of one engine can disturb the rest. A design that is possible in an equation may become unreliable when it requires a forest of engines operating within meters of one another. Larger rockets place increasing stress on their own materials. Tanks must hold propellant while remaining light enough to lift. The lower structure supports everything above it under strong acceleration. A vehicle cannot simply be scaled upward without changing its shape, because mass and strength do not grow in the same way. Eventually, the rocket begins carrying material mainly to support more material. The fuel itself presents another boundary. Chemical engines release energy by rearranging atoms in a reaction. Better engineering can improve efficiency, but it cannot make a chemical bond contain any amount of energy desired. The most effective practical propellants still produce exhaust at limited speed. If the planet requires far more velocity, changing the shape of the rocket cannot fully compensate. On a world several times Earth's mass, chemical rockets may remain possible. They would be larger, more expensive, and capable of carrying less useful material, but a wealthy civilization might still reach orbit. The word impossible becomes appropriate only with care. Physics allows many things that no society can perform regularly, safely, or with resources available at the required scale. Near the upper range imagined for rocky super-Earths, the problem becomes severe. Studies suggest that around 10 times Earth's mass, a chemical launch might still work in theory. Yet the vehicle required for even a modest payload could approach extraordinary size. Beyond that region, conventional designs may stop being a believable route to space, even if no single law of nature draws a perfect boundary. Composition complicates the estimate. A planet rich in iron could be more compact, placing its surface closer to a large amount of mass and deepening the gravity well. A water-rich world might have a larger radius for the same mass, changing surface gravity and escape speed. Without knowing the interior, mass alone cannot tell us exactly how difficult launch would be. Rotation changes the answer too. An eastward launch near a fast-moving equator receives some sideways speed from the planet itself. If the world rotates slowly, that help almost disappears. A civilization could choose the best latitude, the highest safe terrain, and favorable weather. But these improvements would be small compared with the main demand imposed by gravity. The cost would extend far beyond the rocket. Enormous factories would need to refine propellant, build engines, and produce lightweight structures with almost no defects. Roads or waterways would carry components toward a launch site. Tracking stations would monitor the ascent. A single mission might involve a significant share of the planet's industrial ability, turning spaceflight into an event separated by years. Failures would be especially damaging. Earth's launch history advanced through many explosions because another vehicle could eventually be built. On a super-Earth, each attempt might consume so much material and energy that repeated failure threatens the entire program. A civilization could understand how to reach orbit while lacking the economic patience to survive the process of learning. This may delay spaceflight for centuries after the required science exists. Engineers could know the chemistry, calculate the trajectory, and test every component without finding a practical way to assemble the complete vehicle. The barrier would not be ignorance. It would be the difference between knowing that a bridge can be built and having enough material to span an ocean. Perhaps the civilization would begin with extremely small payloads. A transmitter weighing only a few kilograms might reach orbit, followed decades later by a simple camera or weather sensor. Each success would prove that the sky was not completely closed, but the tiny objects would offer little help in constructing the large orbital infrastructure needed to make later missions easier. Reusable rockets could reduce the cost of replacing hardware, though returning them safely would require additional fuel, control, and thermal protection. On Earth, reusability became possible only after launch systems were already mature. Under stronger gravity, reserving propellant for landing means carrying fuel that does not contribute to reaching orbit, making an already difficult ascent harder. Launching from water might allow very large vehicles to be assembled without supporting them entirely on land. High-altitude aircraft or balloons could lift small rockets above part of the atmosphere. These ideas might ease certain problems, but they do not remove the need for orbital speed. Starting a few kilometers higher is useful. Climbing out of a planetary gravity well requires thousands of kilometers of energetic consequence. At some point, the launch vehicle would stop resembling the elegant rockets shown in simple diagrams. It might be a broad structure rising from a reinforced basin, surrounded by cooling systems and protective walls. Its departure would shake the region, fill the sky with exhaust, and consume resources gathered over years. All of this could be required to place an object in an orbit still firmly held by the planet. The civilization might achieve this once, and still remain trapped in every ordinary sense. A flag, a transmitter, or a single crew in orbit would prove extraordinary capability. But a spacefaring society needs frequent access. It must replace failed satellites, deliver supplies, assemble structures, and build vehicles beyond the surface. The rocket equation charges its price every time. Chemical propulsion would therefore become a narrow doorway rather than a broad road. It might permit rare scientific missions while preventing trade, settlement, and exploration on the scale imagined by a civilization looking at the stars. Escaping the surface would be possible enough to inspire hope and difficult enough to keep that hope distant. And before the rocket could even begin paying the full cost of gravity, it would have to force its way through the protective atmosphere that made the planet habitable. At the surface, that atmosphere might feel like one of the world's greatest gifts. It carries warmth away from the equator, softens the cold of night, and allows water to remain liquid across broad regions. It weakens harmful radiation before it reaches the ground, and burns away many small objects falling from space. Every breath, cloud, and ocean depends on gases held close by the same gravity the rocket is trying to overcome. A larger planet can retain more atmosphere over time, though the amount would depend on its history and composition. The pressure at the ground might be only somewhat greater than Earth's, or it could be several times higher. For local life, this would be normal. Bodies, buildings, and machines would develop under that pressure. For a vehicle accelerating towards space, the dense air would become a moving weight that resists every kilometer of progress. Air seems almost empty when we walk through it, but at high speed it behaves differently. A rocket climbing through the lower atmosphere must push gas away from its nose and sides. The faster it moves, the more strongly the air pushes back. Some of the energy produced by the engines becomes heat and turbulence, rather than useful speed, and the vehicle must carry additional propellant to replace what was lost. The obvious solution is to rise slowly while the air is thick, then accelerate after reaching thinner layers. But moving slowly gives gravity more time to pull downward. Engines must continue burning simply to keep the rocket from falling, consuming fuel without adding much orbital speed. Accelerating early reduces those gravity losses, but increases drag and structural stress. Every trajectory is a compromise between two forces that become expensive in opposite ways. During ascent, there is a period when speed and air density combine to place the greatest pressure on the vehicle. The rocket may reduce thrust as it passes through this region, protecting its structure until the surrounding air becomes thinner. On the super-Earth, that dangerous interval could last longer or occur under harsher conditions. The vehicle would need to survive its own acceleration, the planet's gravity, and an atmosphere striking it like a continuous wind. Weather would make the problem less predictable. A thick atmosphere can support strong currents, deep cloud systems, and storms that cover large areas. High-altitude winds may blow in different directions at different levels, pushing against the rocket as it climbs. A launch path, calculated perfectly on the ground, could be disturbed by conditions invisible beneath the cloud deck. The civilization would search for a region where the air is calm, the terrain stable, and the planet's rotation provides useful speed. These requirements may not occur in the same place. The equator offers the largest rotational boost, but it could also contain warm oceans or violent weather. High ground reduces the atmosphere above, yet the planet's stronger gravity may limit the height of mountains. The safest site might not be the most efficient one. An ocean platform could move toward favorable weather and support a very large vehicle before launch. Water would provide distance from cities and absorb some of the sound and heat. But the platform would need to remain stable beneath a rocket whose mass could rival a major structure. Storms, waves, and corrosion would turn preparation into a constant struggle against the environment. The engines themselves would perform differently at the surface than in space. Exhaust expands as it leaves a rocket nozzle, producing thrust more efficiently when the surrounding pressure is low. At high atmospheric pressure, the gas cannot expand as freely. An engine designed for the ground must balance performance against stability, while an engine optimized for vacuum may work poorly or be damaged if used too early. This encourages the use of different stages and engines for different heights. The lower vehicle would be built to survive pressure and produce immense thrust. Upper stages would be lighter, shaped for thin air and vacuum. Each transition would shed mass, yet each would add another separation event that must occur correctly while the rocket moves at enormous speed. Heat would build along the vehicle's surface as compressed air flowed around it. Rockets on Earth manage this with shape, trajectory, and materials that tolerate limited exposure. A denser atmosphere could increase the thermal burden, especially if the vehicle accelerated too quickly at low altitude. Protective material adds weight, and weight returns immediately to the fuel problem below. Sound would carry the launch across a vast distance. Engine exhaust meeting dense air creates pressure waves strong enough to damage nearby structures. The launch complex would require trenches, barriers, cooling systems, and a wide, empty region around it. On a living world where coastlines and lowlands are biologically rich, finding a place for repeated launches might become an environmental and political problem as much as an engineering one. The exhaust would also remain in the atmosphere. A few launches might have little global effect, but a massive program using enormous amounts of propellant could alter local air chemistry, produce clouds, or deposit material across the surrounding region. A civilization living on a stable, carefully protected planet may hesitate to damage that environment in order to reach space. Cleaner propellants could reduce the harm, though fuel chemistry is constrained by energy and storage. Hydrogen and oxygen produce water, but hydrogen is difficult to store and requires large insulated tanks. Dense fuels make smaller tanks possible, but may leave more complex exhaust. Choosing an engine would involve not only performance, but the atmosphere through which it must climb, and the world to which it must return. The atmosphere is not equally dense at every altitude. Pressure falls as the rocket rises, and above most of the air, the drag becomes almost negligible. This is why gravity remains the main obstacle on a very massive world. The atmosphere punishes the early climb, but gravity sets the speed required at the end. Escaping the air does not mean escaping the planet. That difference matters because a thick atmosphere can sometimes help rather than hinder. Balloons might lift scientific instruments and small rockets above the lowest, densest layers. Aircraft could carry launch vehicles to altitude. On a world with substantial air, buoyant platforms might reach heights where the pressure is far lower and the sky darker. Yet a balloon does not provide orbital speed. It can remove part of the drag and begin above storms, but it carries the rocket only a small distance out of the gravitational well. A vehicle released at high altitude still needs nearly all the sideways velocity required for orbit. The improvement could make a difficult launch more practical without turning it into an easy one. Aircraft face a similar limit. Wings use air to create lift, allowing engines to support the vehicle efficiently while it remains within the atmosphere. But as the air thins, wings become less useful. An aircraft cannot simply climb into orbit by flying higher. It must eventually become a spacecraft, accelerating far beyond the speeds at which ordinary aerodynamic flight works. The atmosphere also shapes the return. A spacecraft coming home arrives with enormous energy of motion. Air can slow it without requiring the vehicle to carry all the fuel needed for powered braking. In that sense, a dense atmosphere is valuable. It acts as a vast braking system spread around the planet, turning speed into heat before the craft reaches the ground. But that help is violent. The returning vehicle compresses gas ahead of it until the surrounding flow becomes intensely hot. Stronger gravity may produce higher entry speeds, while dense air increases the forces encountered during descent. A path too steep can crush or burn the vehicle. A path too shallow can carry it back towards space or expose it to heat for too long. Parachutes would open more effectively in dense air, but only after the vehicle had slowed enough for them to survive. The final descent might be gentle compared with the ascent, yet reaching that stage requires precise control through the hottest part of the journey. A civilization could place an object in orbit and still struggle to bring it back intact. This would influence the earliest missions. Disposable satellites may be attempted long before cruise, because nothing needs to survive re-entry. Samples gathered in the upper atmosphere could be transmitted rather than returned. The first orbital achievements might remain entirely one way, with every machine designed to function until it failed and then burn during descent. That one-way approach could slowly build knowledge. A weather satellite would reveal storm systems across the whole planet. A telescope above the atmosphere would see wavelengths hidden from the surface. Communication satellites could connect distant regions without cables or ground towers. Each small success would give society a practical reason to endure the cost of another launch. The atmosphere that resisted the rockets would then become easier to understand from above. Satellites could measure winds, pressure, cloud depth, and changing launch conditions across the globe. Forecasts would improve. Engineers could choose safer paths and narrower weather windows. Reaching orbit once would provide information that made the second attempt less uncertain. More importantly, an object already in orbit would not need to climb from the surface again. It would remain inside the planet's gravity, but it would possess the speed that rockets found so expensive to create. Hardware, fuel, or a small station placed there could become the beginning of an entirely different system, one assembled above the atmosphere instead of forced through it in a single launch. The difficulty is building enough of that system before failures erase the progress. Orbits can decay, equipment can break, and satellites need replacement. If launches occur only once every several years, the oldest machines may fail before the network becomes useful. The civilization would be trying to construct a ladder whose lower steps disappeared almost as quickly as the upper ones were added. Still, the first stable orbit would change the meaning of the sky. It would prove that gravity and atmosphere were not absolute walls, only severe costs. If even a small machine could pass through the air and remain above it, that fragile orbit would become the first place from which the civilization might begin changing the odds. At the beginning, the machine would be alone. It might circle the planet every few hours, crossing from golden daylight into night and back again, while transmitters on the surface waited for its brief passage overhead. Its cameras would return the first complete images of the world. Oceans, storms, continents, and the thin curve of the atmosphere would appear together for the first time. The satellite itself might do little more than survive. Its solar collectors would unfold, its radio would answer, and small devices would keep it pointed correctly. Every system would be tested against radiation, vacuum, and repeated changes in temperature. A failure that would be easy to repair on the ground could end the mission permanently because no second vehicle was waiting nearby. Even a short success would justify another attempt. The satellite could reveal storms before they reached populated coasts, measure changes in the atmosphere, and map the planet without borders or gaps. A later machine might carry a telescope above the clouds, observing wavelengths the air had always blocked. Space would begin providing practical information to the world that had spent so much to enter it. Communication could become one of the strongest reasons to continue. A single satellite in low orbit would pass quickly over each region, but a small network could relay messages across oceans and isolated continents. Ground stations would no longer depend entirely on cables through difficult terrain. The orbital machines would become part of daily life, turning an extraordinary scientific achievement into infrastructure that people noticed whenever it failed. Navigation and precise timing would follow. Signals from several satellites could allow vehicles, ships, and instruments to determine their position. Weather forecasting, agriculture, disaster response, and engineering would improve. Each benefit would create pressure to replace aging spacecraft and launch more capable ones, even if every ascent remained expensive. This is how the orbital barrier might begin to weaken without gravity changing at all. Society would build factories, launch sites, and skilled teams because the machines above produced value below. Experience would reduce failures. Components would become lighter and more reliable. Engines could be manufactured repeatedly rather than as unique experiments. The planet would not become easier to leave, but the civilization would become better at paying the cost. The launch vehicles might remain mostly disposable for a long time. Recovering a stage through the dense atmosphere would require extra shielding and fuel, while landing safely under stronger gravity would add risk. Engineers may choose to lose hardware rather than reduce the already small payload. Reuse would become attractive only when the mass needed for recovery was less damaging than the cost of building another vehicle. Orbit would offer a different kind of reuse. An upper stage that never returned to the surface would not need to survive the atmosphere again. If it could be refueled and maintained in space, it might move payloads between different orbits, visit moons, or carry instruments farther from the planet. The surface rocket would still perform the hardest climb, but it would no longer need to complete every part of the journey. Fuel stored above the atmosphere could change mission design. A vehicle might reach orbit with nearly empty tanks, connect to a depot, and receive the propellant needed to continue. The depot would be difficult to fill because every kilogram initially came from below. Once established, however, it would allow launch vehicles to focus on the surface-to-orbit climb instead of carrying fuel for distant destinations from the ground. The early depot might contain only a small reserve accumulated across many launches. Tanks would need insulation, shielding, and systems to prevent propellant from drifting or boiling away. Connections would have to work in vacuum with extraordinary reliability. A leak could erase years of effort without producing any visible event from the surface. Assembly in orbit would provide another advantage. A large spacecraft would no longer need to fit inside a single rocket or survive one violent ascent as a complete structure. Smaller pieces could be launched separately and joined above the atmosphere. The finished vehicle might be wider and lighter than anything that could rise through dense air in one piece. But assembly requires workers or highly capable machines. Sending people means lifting life support and return systems. Sending robots demands precision, communication, and the ability to handle failures without human hands nearby. The civilization would have to build complexity in the one place where every replacement part was most expensive to deliver. A small moon could become important if the planet possessed one. Leaving the moon's surface would require much less energy because its gravity would be weaker and its atmosphere absent or thin. Minerals gathered there might provide metal, oxygen, and eventually propellant without being lifted from the main planet. The moon could become the source of an orbital industry that the homeworld's surface could not easily supply. Reaching the moon would still demand a functioning space program. Probes, landing equipment, mining machines, and power systems must cross the original gravity well before lunar material helps anyone. The civilization would face the same circular difficulty. Space resources solve the launch problem only after enough equipment has already been launched. Asteroids could offer similar material farther away. Some might contain metals, water, and carbon useful for construction or fuel. Their weak gravity makes departure easy, but finding, reaching, and processing them requires years of orbital experience. A planet-bound society could know that accessible resources exist above, while lacking the initial capacity to use them. The entire effort would therefore depend on continuity. Launches must occur often enough that old satellites do not fail before replacements arrive. Technical knowledge must pass between generations, and political support must survive accidents and economic changes. The orbital network would be less like a single project and more like a living system that dies if maintenance stops. On Earth, Thousands of satellites now operate because launch experience accumulated over decades. A super-Earth civilization might build the same knowledge much more slowly. Its orbital population could remain counted in dozens rather than thousands. Each machine unusually valuable. The loss of one launch vehicle might delay several programs at once. Debris would become dangerous early. A failed satellite does not fall immediately if its orbit remains high enough. Broken pieces continue circling at orbital speed, and even a small fragment can destroy another spacecraft. With few available launches, replacing a damaged machine would be difficult. The civilization would need careful traffic control before its orbital system had become large. Higher orbits might offer longer lifetimes because thin atmospheric gas causes less drag there. Reaching them requires additional energy, but a satellite placed high enough could remain for many years without frequent correction. Engineers would trade launch mass against durability, choosing whether to send a lighter machine into a low orbit or sacrifice payload for a longer-lived path. Eventually, an orbital station might be attempted. It could begin as several modules connected over time, containing instruments and perhaps a small crew. From there, scientists would study the planet, repair nearby satellites, and test equipment without returning everything to the surface. The station would be a permanent foothold only if supplies arrived reliably. Every meal, container of air, tool, and replacement component delivered from below would carry the full price of the rocket equation. Recycling would become more important than comfort. Water and gases would be recovered repeatedly, while waste was treated as material rather than discarded. The station's inhabitants would live above a rich and habitable planet that was unusually expensive to reach and equally difficult to return to. For them, the surface would fill most of the sky. The planet's curved horizon would appear close, its clouds and oceans almost within reach. Yet descending safely through the atmosphere would require careful timing, shielding, and a vehicle prepared long before the crew left. Orbit is close in distance and far in energy, a separation that maps cannot show. If launches stopped, the orbital foothold would fade. Crews would return while fuel remained. Satellites would fail, one by one, and low stations would eventually fall into the atmosphere. Years of progress could disappear without leaving permanent structures above. Gravity would reclaim the machinery not by pulling it down at once, but by making continued support too expensive. If launches continued, however, a threshold might be crossed. Enough equipment could remain in space to repair, refuel, and assemble new systems. Lunar or asteroid material might begin replacing supplies from the surface. The orbital network could become partly independent, reducing the amount of mass that had to climb from the planet for every new mission. This would be the true turning point. More important than a single spectacular launch, spaceflight would stop being a series of isolated objects thrown upward and become an environment where machines stayed, worked, and supported one another. The civilization would still pay heavily to send anything from the ground, but it would no longer rebuild its entire presence after every flight. Reaching orbit would not remove the gravitational well, and it would not guarantee travel to another world. It would create a narrow platform from which different technologies could be tried. Without that platform, every experiment begins beneath the atmosphere. With it, the civilization gains a place where structures can be light, fuel can wait, and the planet's pull is already partly paid. The question would be whether the civilization could maintain that fragile platform long enough for it to grow. A stable, generous planet may reduce the urgency to spend enormous resources above the clouds. Other needs would compete with launch programs that fail often and benefit only a small part of society. The sky could remain scientifically important while never becoming economically central. If that foothold could not be maintained, the civilization would continue to know the universe in extraordinary detail while living almost entirely beneath its atmosphere. its cities might still become vast and advanced. Energy could move across continents. Machines could work beneath oceans, and information could travel around the planet in an instant. Medicine, computation, and material science might develop far beyond our own. Remaining on the surface would not make the civilization primitive. It would describe only one boundary, in a world otherwise transformed by knowledge. Astronomy would begin much as it did on Earth, with careful observation of lights moving through the night. The inhabitants would track moons and planets, predict eclipses, and recognize that their orange sun was one star among many. Better lenses would reveal rings, cloud bands, and distant galaxies. Their gravity would not prevent light from crossing the atmosphere and reaching the instruments below. A thick atmosphere could blur some observations and absorb parts of the spectrum, but engineers would find ways around many of these limits. Telescopes could be built on high plateaus, carried by balloons, or lifted for brief periods by aircraft. Radio waves would pass through useful windows in the atmosphere. Networks of instruments spread across the planet could combine their measurements and achieve clarity no single telescope possessed. They might discover other worlds before placing anything in orbit. A planet passing in front of a distant star would leave a small change in brightness. The movement of a star could reveal unseen companions. Spectra would expose the chemistry of atmospheres many light years away. Somewhere in those measurements, they might find a smaller rocky planet whose surface gravity made spaceflight easier than it was at home. That discovery could create an unusual form of longing. The distant world would be impossible to visit, yet its physical advantage could be calculated precisely. Scientists might know that a chemical rocket launched there could carry far more useful mass than the largest vehicle on their own surface. Another planet would not merely look habitable, it would look open. Public culture could treat space differently under these conditions. On Earth, the sight of rockets, satellites, and people in orbit made the universe feel physically connected to daily life. On the heavier world, space might remain primarily a subject of science, religion, art, and speculation. It would be understood with great precision, while still belonging to a realm almost no one had entered. The few successful orbital missions would become historical events remembered for generations. An image taken above the atmosphere might be reproduced everywhere. A short recording from the first traveler in orbit could remain part of education long after the station itself had fallen. Because each mission was rare, none would become ordinary enough to fade into the background. Failure would carry the same cultural weight. A rocket lost during ascent could end lives and consume resources gathered over years. Public support might collapse after a small number of accidents. The civilization could turn away from crude flight while continuing to launch occasional instruments, deciding that knowledge was worth the cost, but repeated human risk was not. That decision would be rational rather than fearful. The planet below may be unusually stable and rich. There would be no nearby empty world that offered better conditions than home, and no disaster forcing immediate migration. Spending a large part of global industry to place a few people above a perfectly habitable surface could appear wasteful even to a society fascinated by the stars. The absence of urgency could last for thousands of years. A long-lived star would change slowly. Oceans would remain broad, the atmosphere protective, and the biosphere capable of recovery. On Earth, space settlement is sometimes imagined as insurance against planetary catastrophe. On a world more stable than ours, that argument might feel distant until the technology needed to act had already remained neglected for centuries. There would still be dangers, impacts, disease, climate shifts, or the civilization's own technology could threaten life. Satellites would improve warning and response, but a weak orbital program might limit planetary defense. An asteroid could be detected years in advance without a practical way to move enough equipment beyond the atmosphere to change its path. This would make confinement visible at the worst moment. A society may understand a threat completely and possess enormous power on the ground, while lacking access to the place where intervention must occur. The barrier would not hide the danger. It would allow the civilization to watch it approach through instruments that could describe every detail. Yet most generations would not live under such a threat. They would build lives within an environment large enough to feel endless. Continents, oceans, and deep layers of the planet could provide room and resources for a long time. Expansion might move downward, underwater, or into artificial habitats on the surface rather than outward into space. High gravity could even shape their idea of travel. Flight through the atmosphere might remain impressive because lifting heavy vehicles requires energy, while orbital flight sits in another category entirely. Words associated with leaving the world could carry meanings closer to disappearance than transportation. The sky would be crossed by weather and aircraft, but rarely by anything that did not return. Their communication with other civilizations, if any were found, would not require physical escape. Powerful radio or optical transmitters could send information towards the stars from the ground or high atmosphere. A planet unable to launch large spacecraft might still announce its existence across hundreds of light years. Intelligence could travel where bodies could not. This creates a strange possibility for distant observers. We might detect a clear artificial signal from such a world and assume that its makers possess fleets, stations, and probes. In reality, the transmission could come from a civilization that has never maintained a crew in orbit. Its understanding of the galaxy might be deep, but its physical presence would end near the upper edge of its own atmosphere. If it received a signal from elsewhere, the response might strengthen its connection to the universe while making the confinement more obvious. Messages could cross interstellar distance, carrying images of moons, machines, or habitats built by a civilization born on a lighter planet. The trapped society would learn that spaceflight was not universally difficult. Its own world had set a higher price. That knowledge could revive efforts to leave. Research programs might continue across generations, not because one design promised success, but because every conventional path had reached the same limit. Engines could become more efficient. Materials could become stronger. Rockets could grow larger. Progress would narrow the gap without removing the exponential cost at its center. Over time, the civilization may stop measuring success by Earth-like milestones. It would not need to reproduce a particular kind of rocket or follow the same sequence from satellite to crewed moon landing. Its technology grew under different pressures. The path into space might begin with machines placed high in the atmosphere, energy sent from the ground, or structures assembled through methods that seem unusual only from our history. The problem could attract the planet's greatest minds for centuries. Physicists would search for propulsion with more energy than chemical reactions. Engineers would study long tethers, magnetic acceleration, and vehicles powered from outside rather than carrying everything aboard. Some proposals would fail because the required materials did not exist. Others would wait for an orbital foothold too difficult to construct. Political systems would have to plan beyond a single lifetime. A new launch method might require infrastructure spread across a continent, or a structure assembled over many decades. No one generation could complete it alone. The project would succeed only if later societies still valued the goal and trusted the decisions made by people long gone. There could also be opposition. A machine capable of accelerating spacecraft to enormous speed could be used as a weapon. Energy systems built for launch might consume resources needed elsewhere. An orbital tether or giant tower could fail over populated land. The route out of the gravity well would create risks on a planet that had remained habitable without it. Some cultures might decide that leaving is unnecessary. They could view the surface as the proper home of life and interstellar communication as enough. Others would argue that a civilization dependent on one planet remains vulnerable no matter how stable the world appears. The disagreement could continue long after the technical question was understood. This is where the idea of being trapped becomes less simple. A civilization is not trapped merely because escape is expensive. It becomes trapped when every available method costs more than society is willing or able to sustain. The boundary is built partly by gravity and partly by choices made under that gravity. From outside, we might never know where that boundary lies. Telescopes could detect atmospheric industry, artificial light, or deliberate radio signals without seeing any objects leave the planet. The absence of probes would not prove a lack of intelligence. It might reveal a world whose inhabitants developed inward, because outward movement remained the most difficult thing they could attempt. Night after night, their astronomers would continue watching the stars. They could map the galaxy, study the beginning of the universe, and know the composition of worlds that no living traveler had approached. Knowledge would make the sky familiar, but familiarity would not make it accessible. To cross that final boundary, they would need to stop treating launch as a larger version of an ordinary rocket and begin building an entirely different path into the sky. The most direct change would be to use a source of energy more powerful than chemical combustion. Nuclear reactions release far more energy from the same amount of material, making them attractive for deep space travel. Yet, using that energy at the surface is difficult. A launch engine must produce enormous thrust immediately, remain light, and operate safely beneath a vehicle filled with passengers or delicate machinery. A nuclear thermal rocket could heat propellant to extreme temperatures and expel it at greater speed than many chemical engines. In vacuum, this may allow efficient travel between planets. On the surface of a super-Earth, however, the reactor, shielding, and cooling systems would add mass. An accident during launch could spread radioactive material through the atmosphere, turning each attempt into a risk for the inhabited world below. More advanced nuclear systems might eventually perform better, but greater energy does not automatically produce a practical launch vehicle. The engine must channel that energy without melting itself. Materials must survive heat, vibration, and pressure, while remaining light enough to lift. A civilization may understand the reaction long before it can build a machine capable of controlling it through the entire ascent. Another approach would leave the heaviest power source on the ground. Instead of carrying all its energy as fuel, a vehicle could receive a beam from the surface. Powerful lasers or microwaves might heat propellant, drive an electric system, or push against a specially designed sail. The craft would become lighter because the generators, cooling equipment, and much of the machinery remained below. The beam would need to follow the vehicle with extraordinary accuracy. Clouds, rain, and the movement of the atmosphere could scatter or absorb part of the energy. A dense sky that protects life may be poorly suited to transmitting a concentrated beam upward. Several stations spread across clear regions could take turns as the craft moved, but the system would have to remain aligned while accelerating rapidly toward the horizon. For a small, unmanned payload, beamed energy might be enough to create a narrow route into orbit. A lightweight vehicle could carry little more than propellant and guidance equipment, receiving power from a vast array below. Once the method worked, it might send components toward an orbital construction site far more often than giant chemical rockets could. The ground installation would be enormous. It would require energy generation on a planetary scale, precision optics or antennas, and a protected path through the sky. The same beam capable of driving a spacecraft could destroy anything that crossed it accidentally. Weather, wildlife, aircraft, and populated areas would need to be kept away from the launch corridor. Electromagnetic acceleration offers a related possibility. A long track could pull or push a vehicle forward without burning fuel on board. On the ground, the track might follow a mountain range or rise along an engineered structure, accelerating a payload before it entered the open atmosphere. The vehicle would leave the end already moving at great speed, reducing the work required from its engines. But reaching orbital speed close to the surface creates its own danger. Dense air striking a vehicle at several kilometers per second produces extreme heat and shock waves. Passengers would also experience heavy acceleration unless the track extended for a very long distance. A system gentle enough for living crews could span hundreds or thousands of kilometers, demanding precision across a structure larger than many nations. The accelerator might work better inside a tunnel, from which most of the air had been removed. The vehicle could gain speed in near vacuum and emerge high above the surface through a carefully placed exit. Building and maintaining such a tunnel under strong gravity would be a planetary engineering project. At the opening, the craft would still meet the atmosphere suddenly, unless the path ended at extreme altitude. High-floating platforms could remove part of that difficulty. Vast balloons or buoyant structures might carry launch equipment above much of the weather. From there, a rocket or beamed vehicle would begin in thinner air, avoiding the heaviest drag near the ground. The platform itself would not remove gravity, but it could serve as a permanent port between the surface and the upper atmosphere. Supporting a large launcher on a floating structure would be difficult. The platform must remain stable while fuel, engines, and cargo are assembled. Winds would move it, electrical storms could threaten it, and every kilogram lifted to the platform still begins on the ground. Yet, unlike a rocket, a buoyant system does not need to burn fuel simply to remain aloft, making slow transport to altitude possible. The most familiar dream is a space elevator, a cable extending upward from the equator and held tight by a counterweight beyond a high orbit. Vehicles could climb the cable using energy, rather than carrying enough propellant to accelerate themselves to orbital speed. On Earth, even this design demands materials stronger and lighter than anything available for a complete structure. On a heavier planet, the tension would be greater and the cable might need to extend much farther. The material requirements could become impossible for any known substance. A thicker cable adds weight, which creates more tension and requires still more material. The same problem that enlarges rockets would reappear in a different form along the entire length of the structure. An orbital ring or active launch loop could avoid some limits by supporting itself through motion rather than relying only on the strength of a stationary cable. Fast-moving material inside a guided structure could hold part of the system above the planet, creating platforms high in the atmosphere or beyond it. Vehicles might climb electrically and enter orbit without carrying most of their fuel. Such structures are physically conceivable but far beyond ordinary construction. They require continuous control, immense energy, and stability across planetary distances. A serious failure would not be confined to a launch pad. Sections of the system could fall across thousands of kilometers, making the path to space dangerous to the surface it was built to serve. A rotating tether already in orbit may be a more gradual step. The long cable would spin around its center, allowing one end to dip toward the upper atmosphere at the right moment. A vehicle rising from below could connect to it, and the tether's motion would pull the payload upward while transferring some of its own momentum. After releasing the payload into a higher orbit, the tether would slow slightly and need to restore its motion through propulsion or interaction with other spacecraft. It would not create energy from nothing. Its advantage is that the heavy system remains in space and can assist many lighter vehicles, reducing how much speed each one must produce with onboard fuel. Studies of this idea suggest that a well-designed tether could cut a substantial part of the velocity required from a super-Earth launch vehicle. A reduction of even a few kilometers per second matters greatly, because rocket mass grows so quickly with required speed. The tether does not need to eliminate the gravity well. It only needs to remove enough of the climb to bring chemical rockets back into a practical range. But placing the tether in orbit requires the kind of launchability it is meant to improve. The civilization would have to send cable, control systems, power equipment, and perhaps many replacement sections through the atmosphere before receiving any benefit. The first tether could demand years of launches and then fail before it had repaid the effort. A smaller experimental system might grow gradually. Short tethers could move tiny payloads between orbits. Later versions could become longer, stronger, and capable of reaching lower into the atmosphere. Materials recovered from a moon or asteroid might expand the structure without being lifted from the main planet. The doorway would open through accumulation rather than one enormous leap. Different technologies could be combined. A balloon might carry a small rocket to altitude. A ground beam could power the early acceleration, and a rotating tether could collect the vehicle before it reached full orbital speed. No single system would solve everything. Together, they could divide one almost impossible launch into several difficult but manageable stages. This layered path may be how a heavy world civilization finally becomes spacefaring. The process would take longer than building a larger rocket, but it would create permanent infrastructure. Once beams, platforms, and tethers operated regularly, the cost of each later journey could fall. The planet's gravity would remain unchanged while its practical hold weakened. Even then, escape from the planetary system would not follow automatically. Stations, probes, and ships would need to be built beyond the atmosphere. Long journeys would require energy, shielding, and life support. The inhabitants would have solved the barrier closest to home, only to meet the much larger distances between worlds and stars. Whether they ever reach this point would depend on more than intelligence. The planet must provide accessible materials, stable institutions, and enough surplus energy to support projects lasting generations. A war, economic collapse, or change in priorities could interrupt construction. The laws of physics might offer a path that history never allows the civilization to complete. From Earth, the difference would be almost impossible to see. A society building a planet-wide launch system could appear as a faint change in atmospheric chemistry or heat. A society that abandoned the attempt might look nearly identical. We could detect life and perhaps radio communication while finding no evidence of objects moving between planets. The silence of space around a habitable world would not tell us that nothing intelligent lived below. It could mean that rockets were too inefficient, tethers never survived, or the immense structures required for escape were never worth their cost. And if even these paths remained beyond reach, the galaxy could contain intelligent worlds that never became visible through ships, probes, or colonies at all. Our picture of an advanced civilization is often shaped by movement. We expect it to spread beyond its planet, build stations around other worlds, send probes between stars, and leave large structures that telescopes might notice. Once intelligence learns the laws of nature, expansion can seem like an inevitable step. Yet that expectation comes from a species born on one particular planet, where the first route to orbit was difficult but possible with chemical fuel. On a heavier world, intelligence could lead somewhere else. The civilization might build powerful computers, understand biology in extraordinary detail, and control energy across its surface without developing routine launch. It could become old and stable while remaining concentrated below the atmosphere. From a distance, nearly all of its achievements would be hidden inside a single point of light. A telescope on Earth would not see cities directly. It might detect gases in the planet's atmosphere, changes in reflected light, or unusual heat, but every interpretation would be uncertain. Industry could produce chemicals that nature rarely creates in large amounts. Artificial illumination might slightly brighten the night side. These traces would be faint, and a careful or efficient civilization might produce very little of them. Radio signals could escape the gravity well because light does not need a rocket. A transmitter on the surface can send energy outward at the speed of light, passing through the atmosphere at suitable frequencies and continuing between stars. The civilization might speak across the galaxy long before it could place a person in orbit. Information would become its only form of interstellar travel. But radio does not guarantee detection. Most communication may use low power, cables, or narrow beams aimed between known locations. Signals spreading in every direction become weak very quickly. Earth could lie outside the beam or listen at the wrong time and frequency. A world full of technology could therefore appear radio silent unless its inhabitants deliberately announce themselves. They may have little reason to do so. If spaceflight never became practical, the idea of contact could feel remote and one-sided. A message sent to another star might wait centuries for an answer. The civilization could choose to observe rather than transmit, or focus its energy on a planet already rich enough to occupy its attention for millions of years. This does not solve the mystery of cosmic silence, but it changes one assumption behind it. The absence of visiting probes does not necessarily mean the absence of intelligence. Some civilizations may lack the practical route from knowledge to physical expansion. Their worlds could support life exceptionally well, while making the first step away from life's surface unusually expensive. Even a successful orbital program might remain too small for interplanetary settlement. A civilization that can launch a few satellites is not automatically able to lift habitats, factories, and thousands of people. The mass required for a self-sufficient colony would be enormous. If every kilogram leaving the surface demands a vast launch system, settlement could remain beyond reach long after scientific probes become possible. Robotic exploration would be easier, but still limited by the same bottleneck. Small probes could visit moons and neighboring planets, returning images and measurements. Sending enough machines to build industry elsewhere would require repeated launches. The civilization might know its planetary system intimately, while leaving almost no permanent machinery beyond its home world. Interstellar probes would be harder again. The vehicle must not only escape the planet but also survive decades or centuries, accelerate to a useful fraction of light speed, and communicate across growing distance. A society that spends extraordinary resources merely reaching orbit may see the stars as destinations for signals, not spacecraft. From Earth, such a civilization would leave none of the signs often imagined in searches for large-scale technology. There might be no unusual objects passing in front of its star, no enormous collection of solar energy, and no network of probes moving through nearby systems. The planet could be biologically and intellectually rich, while appearing almost natural. This raises a deeper problem of selection. We search most easily for what changes the environment on a large scale. Loud radio beacons, industrial gases, artificial heat, and giant structures are detectable precisely because they are difficult to hide. Quiet technologies, efficient societies, and civilizations confined to one world leave weaker evidence. Our methods may favor the most visible cultures rather than the most common ones. The planets easiest for life to occupy may therefore be among the hardest for us to recognize as technological. A stable world does not need constant engineering to remain comfortable. Its inhabitants may use less energy to control climate, build fewer artificial habitats, and feel less pressure to move elsewhere. The planet's generosity reduces some of the traces we expect progress to create. By contrast, a difficult planet might force technology into the open. A thin atmosphere could require sealed cities. Weak sunlight might lead to enormous energy collectors. An unstable climate could produce visible engineering on a global scale. The world less suited to life could become easier for distant astronomers to identify as inhabited by intelligence. Habitability and detectability do not rise together. A planet can be good for biology and quiet in the sky. Another can be dangerous, heavily engineered, and obvious. If we search only for civilizations that reshape their systems or travel between stars, we may overlook those that found long-term survival without either. Time makes the search harder. A planet-bound society could use detectable radio for only a short period before switching to more efficient communication. Its bright technological phase might last a few centuries inside a civilization millions of years old. Earth would need to observe during that narrow window, while the signal itself crossed the correct distance between the worlds. Spacefaring civilizations also have limited visible periods, but expansion can spread their traces across several locations. A probe or colony might continue after the original planet changed. A society confined by gravity leaves almost everything at one address. If its technology becomes quiet or the civilization ends, the system can return to an apparently natural state. The galaxy may therefore contain worlds that became intelligent and disappeared without sending a single machine beyond their moons. Their languages, discoveries, and histories would remain on the surface until weather and geology erased them. No probe would carry their records outward. Unless a radio signal happened to cross another listener, the universe would preserve almost nothing of their existence. That possibility is unsettling because it makes intelligence less permanent than the planet that supports it. A stable super-Earth may remain habitable for tens of billions of years, yet many civilizations could rise and disappear on its surface without ever escaping. The world would continue circling its quiet star, capable of producing life again, while showing no clear sign of those who once understood the sky. We might already be observing such a planet. Its mass and radius could be listed in a catalogue. Its orbit might place it within a region where liquid water is possible. Telescopes could spend years measuring its atmosphere and still fail to separate technology from nature. A civilization might be looking back through instruments of its own, equally unable to cross the distance in matter. In that situation, both worlds could know that the other may be alive, while neither produces the evidence needed for certainty. Their radio beams may never align. Their technological periods may occur thousands of years apart. Gravity would be only one of many barriers, but it would prevent the physical traces that might otherwise survive the mismatch in time. This gives the silence between stars a less empty meaning. Silence can contain planets whose inhabitants do not transmit, cannot launch, or never build on a scale visible from far away. It can contain extinct civilizations whose worlds remain habitable, and new intelligence that has not yet developed technology. A quiet system is not evidence of a lifeless one. Still, gravity cannot explain every absence. Many potentially habitable planets may be similar to Earth or smaller. Advanced propulsion could overcome barriers that appear severe to us. Civilizations could choose expansion even when it is difficult. The idea of trapped worlds is one possibility among many, not a complete answer to why no unmistakable alien technology has been found. Its value lies in changing what we expect. Intelligence need not produce starships. It need not cover a solar system or leave artificial objects around neighboring stars. A species can understand the galaxy without entering it, just as a person can understand an ocean without crossing it. The achievement is real even when the boundary remains. Future telescopes may be designed with this quieter possibility in mind. They could search more carefully for atmospheric chemicals, changing heat patterns, brief radio leakage, or illumination that follows a planet's rotation. None would prove a spacefaring society. They might reveal something more common, technology concentrated on a world that still looks mostly natural. If such evidence were found, the planet's mass would take on new importance. Astronomers would estimate surface gravity and escape velocity, asking whether the inhabitants could reasonably reach orbit. A measurement once used mainly to describe geology would become part of the story of what the civilization might or might not be able to do. The comparison would inevitably return to Earth. Our planet is large enough to support oceans and atmosphere, yet small enough that chemical rockets can carry useful payloads into orbit. This balance may not be unique, but it should not be assumed. Before we call those distant worlds silent, it is worth asking why our own planet made the opposite path possible at all. Earth is not a gentle world in every respect. Its climate has moved through long ages of ice and heat, yet beneath that instability lies a balance that is easy to overlook. The planet is heavy enough to hold a substantial atmosphere, warm enough for liquid oceans across immense spans of time, and active enough to keep reshaping the materials at its surface. At the same time, it is not so massive that the sky became a permanent ceiling. That combination was never arranged for us. It emerged from the ordinary violence of planet formation, from collisions between young worlds and the slow gathering of rock around the infant sun. Earth ended with roughly the mass it has, at roughly the distance where water could remain liquid, beneath a star steady enough to give evolution time. None of these conditions is perfect on its own. Together, they created a world where complex organisms could appear, where hands and minds could build machines, and where those machines could eventually climb beyond the atmosphere. The climb is still severe. To leave Earth entirely, an object must reach an escape velocity of about 11.2 kilometers per second. Although rockets do not simply accelerate to that speed in a single straight rise. Reaching a stable low orbit requires something closer to 7.8 kilometers per second of sideways motion, along with additional effort lost to gravity and the atmosphere. Those numbers are difficult to feel from the ground. A passenger aircraft seems fast, yet an orbiting spacecraft travels many times faster, not because space is far away, but because staying there means falling around the curve of the planet without touching it. Chemical rockets can just manage this while carrying something useful. Most of a launch vehicle is propellant, and much of the rest is structure needed to contain it. Only a small fraction reaches orbit as payload. The towers, fire, and deep vibration of a launch can make the event look like an expression of overwhelming power. But in engineering terms, it is closer to a narrow negotiation with gravity. Every kilogram matters. Every stage is discarded when its empty tanks become a burden. The rocket succeeds by becoming lighter almost as quickly as it rises. Earth allows that negotiation to end in our favor. Its pull is strong, but not beyond the range of fuels that release energy through chemistry. A somewhat larger rocky planet could offer life a deeper ocean, a thicker atmosphere, and a climate less easily disturbed. It might remain comfortable for longer than Earth does. Yet each improvement could quietly deepen the gravitational well. The same mass that protects a biosphere would demand more fuel from a rocket, and the added fuel would require stronger tanks and larger engines, which would themselves add mass. The difficulty does not rise in a simple, forgiving line. Here, the atmosphere also happens to play two opposing roles without completely winning either one. It shields the surface from much of the harmful radiation arriving from space, burns away countless small objects before they reach the ground, carries water through the climate, and makes open-air life possible. For a rocket, however, the atmosphere is an obstacle. It produces drag, shakes the vehicle, and forces engines and structures to survive a passage through dense moving air. A far thicker atmosphere might be comforting at sea level and punishing during launch. Earth's air creates danger and loss, but it thins quickly enough for a well-designed vehicle to pass through. Even the rotation of the planet offers a modest gift. Earth turns eastward, carrying the surface with it. A rocket launched in the same direction can begin with some of that speed already supplied, especially near the equator, where the ground moves fastest. This is why launch locations and flight paths matter. Rotation does not make orbit easy, and many missions cannot use its full advantage, but it reduces the price for certain journeys. On a slowly rotating world, or one locked with the same face toward its star, this small assistance might be absent. Above the atmosphere waits another fortunate feature, a large moon close enough to visit with machines built only a few generations after the first powered aircraft. The moon did not pull humanity into space by itself, but it gave the early space age a clear shore to aim for. It was distant enough to demand new systems and near enough for radio signals to cross the gap in little more than a second. Its surface offered a place to land, measure, collect, and leave again, turning abstract spaceflight into a destination that could be seen from almost anywhere on Earth. There were advantages on the ground as well. Earth gathered accessible metals, carbon-rich fuels, radioactive elements, water, and a wide range of chemical materials into its crust. Geological activity exposed and concentrated some of them. Rivers, coasts, and relatively stable land supported large societies, while fire and later electricity allowed those societies to work matter at increasingly high temperatures and pressures. Rockets did not emerge from intelligence alone. They required mining, manufacturing, precise instruments, enormous energy, and institutions able to support experiments whose usefulness was uncertain. When rockets finally appeared, Earth did not seem welcoming. Early vehicles exploded, tumbled, broke apart, or failed to ignite. Engineers discovered that vibrations could destroy components that worked perfectly on a test bench, that pumps had to move fuel with astonishing speed, and that guidance errors lasting only moments could end a mission. People died on launch pads and inside spacecraft. The route through the sky existed, but it was so narrow that finding it required repeated failure and a willingness to return. Seen from that history, calling Earth easy to escape would be misleading. It took industrial civilization, advanced mathematics, global supply chains, and vast public spending to place even small objects in orbit. Human beings have walked on another world, but only briefly. Most people who have ever lived never traveled more than a few hundred kilometers from their birthplace, and nearly every living person remains at the bottom of the same gravitational well. We are not free of Earth. We have only learned that the boundary can be crossed. That distinction matters when thinking about worlds larger than our own. An intelligent species under stronger gravity might understand orbital mechanics perfectly. Its scientists could watch moons circle overhead and predict eclipses centuries in advance. They might build telescopes able to map neighboring planets, detect the atmospheres of distant worlds, and recognize that life could exist elsewhere. Knowledge would tell them where the road leads, but it would not provide the energy needed to travel it. Their first launch attempts might resemble ours in spirit, and fail for reasons that no improvement in courage could remove. Vehicles would need more propellant, larger structures, and engines operating closer to material limits. A dense atmosphere could add another burden, while high pressure might make lightweight construction unusually difficult. At some point, the project would stop being merely expensive and begin to compete with the foundations of civilization itself. A society could decide that observatories, medicine, climate control, or life beneath the sea deserved the resources more. Earth gave us enough margin to begin without that infrastructure already waiting. Crude rockets could reach the upper atmosphere. Better ones could place small payloads in orbit. Successive generations then used what they had learned to lift satellites, stations, telescopes, and probes. The sequence was expensive, but it could grow one achievement at a time. A heavier planet may demand something close to the mature system at the very beginning, before its people have gained the experience that such a system requires. This makes our planet's ordinary appearance slightly deceptive. Earth is not the largest rocky world, nor the calmest, nor necessarily the most enduring home life could find. Its atmosphere is not especially thick, and its climate has never been perfectly stable. What it may possess is a useful imperfection. It protects life without enclosing it completely. It holds oceans without placing their surface too deep inside gravity. It gives technology resistance, enough to make escape difficult, but not so much resistance that the attempt becomes unreasonable. If Earth had formed with considerably more mass, human history might still contain cities, music, science, and long nights spent studying the stars. The constellations would remain overhead, and the laws governing them could still be discovered. But there might be no artificial lights moving among those constellations, no footprints on the moon, and no instruments drifting beyond the outer planets. the universe would be understood from a distance, while our own atmosphere remained the highest place any human creation could reach. A slightly smaller Earth would bring different risks. It might lose atmosphere more easily, cool internally sooner, or struggle to preserve surface water over geological time. The planet could be easier to leave and harder to live on. That is the deeper tension hidden inside the search for another home. The qualities that support life and the qualities that support departure are related, but they do not always point in the same direction. A world can be generous to biology and severe toward machinery. So the phrase habitable planet may conceal more than it reveals. It tells us that conditions might allow liquid water, suitable temperatures, and perhaps a stable environment. It says little about whether the inhabitants could reach orbit, maintain satellites, or send evidence of themselves between the stars. A planet that looks like a better Earth through a telescope may be better only for those who never try to leave it. That possibility changes the silence of the galaxy without solving it. Some distant civilizations may be absent because they never arose, others because they did not survive, and some because they chose not to announce themselves. There may also be societies living on rich, heavy worlds, listening as carefully as we are, aware that the universe is filled with destinations they cannot touch. Their skies would not be empty. They would be boundaries. For now, every spacecraft leaving Earth carries evidence of a balance we inherited rather than earned. The pale exhaust rising over a launch site is not only a display of human engineering, it is also a sign that the planet beneath the engines permits the attempt. Gravity pulls, the atmosphere resists, and still there is a path through both. Narrow, costly, and dangerous, it remains open. That may be Earth's quiet advantage. Not that it is the finest possible home, but that it lies near a threshold where a living world can eventually look outward and place something beyond itself. We were born deep enough in gravity to have air, oceans, and long biological time, yet not so deep that the rest of the universe became unreachable. Our first steps into space may therefore say as much about the planet that formed us as they do about the species that built the rockets. Somewhere, beneath a heavier sky, another intelligence may be reaching the same understanding from the other side. It may know the age of its star, the chemistry of nearby worlds, and the enormous distances between them. It may even detect the faint signals of planets like ours. What it cannot do is follow. The thought is unsettling not because such beings would be less advanced, but because their knowledge could be as wide as the galaxy, while their physical horizon remained close. And here, on a world that is neither perfectly safe nor completely confining, we continue to rise through the thin opening available to us. Each launch is brief, and from far away it would be almost invisible. Yet, it marks a rare kind of movement, matter from a living planet crossing the boundary that shaped it, carrying memory, instruments, and questions into the dark. Thank you for watching this calm journey into the hidden gravity of habitable worlds. If you enjoyed this documentary, subscribe for more quiet space stories like this. Leave a like if you want more deep journeys into the mysteries of the universe. And tell me this, would you choose a safer, more habitable planet if it meant no one could ever leave? Or would you choose Earth and keep the road to space? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you were watching the Just About Space channel, talking about why the most habitable planets may be impossible to escape. Sleep well and keep looking up. Good night.